Okay, I think your sections should be continued by this slide. So I tried to finish up this chapter by today. Okay, so if you look at this figure here, it shows um, for a typical nation building type here, there are three common types, which is the first one is a flat roof. You can see here the flat roof here is like a slabs. Okay, so that means how the load transfer to the beams, to the roof beam, it's similar as a slabs distribution. So let's say this is the beam here along the sides here, four sides of the beams here that will support the roof. Okay, so that means you can just consider this flat roof as a slabs. Determine the type of this slab, either one way or two way slab. So kalau one way slab just distributes the loads to these beams and distributes the load to these beams. Okay, so kalau two way it should be a portion for triangle, a portion for trapezium, which is the load distribution same as for the slabs distributions. Okay, then it also have a hip roof and gable roof. So actually this a type of roof for the hip and gable roof. It consists of a truss member inside it that will hold support all the metal deck systems here. Okay, this gables roof also will have several numbers of truss member, depends the spans of the buildings. So for this truss member, okay, if I sketch it for one truss member, it will have a member in compression or member in tension. Whereas the roof system here, for example, the metal decks, the purlin battens, or any services will be pointed as a point load. Okay, normally exactly uh, at the point of this truss member. Okay, so then it will transfer point load to the beam. Okay, same for these two types of roof, hip roof and also gable roof. Okay, because it consists of a truss member. So the load will transfer as a point load, while for the flat roof it transfers per area, which is similar as slab load distributions. So the load that carried by the roof system here basically it still have a loading of permanent action, which is GK and also QK, but what's the loads come from? Okay, GK here, or permanent actions or permanent loads, it come from roof tile or metal decks, insulations, okay, piping system, air conditions. Okay, so that's all about insulation. Safe weight of truss. So if this truss made of steels, it should be multiplied with the unit weight of steel or timber, right? So and then have a batten or purlin. So if you look at here, this is all the battens, purlin that will supports the metal deck system here. Okay, because the metal decks have small lengths, right? Have a short length here. That's why we have to arrange these purlins according to the length of the metal deck here. Okay, Then have a shillings here. This is the shilling that also is supported by the roof, by the trusses, and then also any services. This is all that will be considered as a GK. Okay, and then for variables actions, QK, or imposed loads, which is it considered just for maintenance purpose. Okay, for repair, zinc mana yang bocor, zinc yang tercabut kan, nak betulkan area, so that is a maintenance purpose, which is at one time only one or two workers will be climb up on the roof for repairing works and so on. Okay, that's why the variables actions or QK is quite small here, just within 0.75 up to 1.25. So that means for design estimation, you can select any value between this range. Okay, so this is how to calculate the load distribution for the roof systems. Okay, for example, whole form steel truss system with the spans less than 13 meter here. Okay, so if you look at here, it's so many purlins or batons here. Okay, according to the length of metal decks that will be arranged on top of it, right? Okay, so if you look at from the top view here, from the top view, you will see just a flat surface, okay, which consists of numbers of purlins and metal decks here. So that's why it's quite simple here. If you want to calculate the load that will be carried by the roof beam, okay, by the roof beam especially, that will support only the truss system, okay, that only support the truss system. It don't have any slabs. Normally there's no any slab. Okay, so this is how to calculate the distributions from the roof system, which is you can just consider half of the load that will be supported by this beam, and then half of it will support by this beam, and same goes for other side. So 0.5, okay, from the load, this is either GK or QK. Okay, what is GK? It comes from survey of trusses, any insulation services, shillings, metal decks. Okay, that is GK of the roof truss. Kalau QK, it's just about its maintenance, between 0.75 to 1.25 here. Okay, and then LX, dia punya short length lah. Okay, so same goes for any direction or any beam that you want to design. Then for the hot roll steel truss system, which have a truss system here. Okay, so that means the load will be pointed at the columns, or might be if the frame arranged on the beams, it will be pointed at the beam here. Okay, depends how the engineer, the designer design the roof system. But normally for the safety, we arrange the truss member here, okay, exactly at the column. So that means the load will be applied directly to the columns. Okay, so this is how we do the load distributions for the roof, which is this is the load that is from GK or QK. Normally will be pointed at the what we call it as a point here, okay, between the members. Then you need to come up with the value of reactions, okay, for the reaction. This analysis of truss analysis you've already learned in the structural analysis, right? In from your previous subjects. Okay, so then this is how the columns, okay, will support all the load from all the sides of the beam. For example, column A. So column A have two sides of beams, okay, the right side and then the left side. The left side have two spans. So this is examples of the left sides of continuous beam. It has a two spans here. So this is R1, this is R2, and then this is R3. That means the reactions from the R3 will be distributed to the column A. Okay, R2 will distribute to this columns, and R1 will apply its load to this column. So that means for the column A will support the load from R3 and also another one from the right side continuous beam that have a three spans here. This is the three span of the right directions, okay, of continuous beam. So that means R1 also will apply its load to the column. So column A will support R3 and also R1. So same goes for other intersections here. Depends how many a beam will cross, okay, will be supported by that columns. Okay, then we go for structural analysis. So you can refresh balik apa yang you dah belajar dalam structural analysis. I will not go deep into it. So I will not go detailed into it. Okay. But the basic thing is structural analysis is a combinations of all the loads. So we have a GK, QK and also WK. Tapi mostly our examples kita tak consider about the WK because we just design for a common building. You punya project pun sampai double story building. Okay, so we just consider for the for calculation for load estimation of GK and QK. Okay, so you need to know how we do the arrangements of the loadings, okay, in terms of load combination, which is combinations of GK and also QK. This is example for the simply supported beam. It's just one span here, so that's why we call it as a simply supported beams. So it will be loaded with the maximum load here. So the maximum load is calculated by these equations. I put a star here. Okay, this is very important. You need to remember of this equation, which is it consider the safety factor here, which is 1.35 safety factor for GK and 1.5 safety factor for QK. So you just imagine GK, QK ni the original load of GK, original load of QK, which is 100% load that we calculate based on the materials, based on the purpose or function for that structure. Then we add another safety factor. Remember we go for a safety, right? So it's like a 135% another safety factor. Okay, we consider for the GK and another 150% that we consider for the QK. So this is an example for the uniform loads. Okay, and there are some cases, okay, that have a point load also for that span. So this point load, it can be from the secondary beams. Remember what is secondary beams, which is it crossings, it's support by beam to beams. Okay, so it might be from the columns, or might be from the truss reaction, the truss systems reactions, right? That appointed the beams by its point load here. So from this simply supported is quite simple, which is from it you need to come up with bending moment diagrams, right? In order to know what is the maximum moment here. And also come out with the shear force diagram. What is the Vmax? What's the Vmax here? Either by equations or by reactions. Okay, what's the reaction for the supports according to the load that apply on it? Then you can plot the bending moment diagram and shear force diagram. So Vmax and Mmax here, moment max, is very important for you to use to apply in order to provide the main reinforcement, okay, and also this is to provide the main reinforcement for the bending moment, while for Vmax is required in the design for the shear links, okay, for the shear links. So how big the value here, how high or small the value here will affect, okay, the numbers of reinforcement, dia punya sizings, dia punya diameter, right? So according to the moment max and also Vmax. Okay, but for continuous beam, so nama pun continuous beam, so that means it will have more than one span. It can be 2 spans, it can be 3 span, as long as it's more than one span, it considered as a continuous beam. So kalau simply supported is quite simple, right? So simply supported is quite simple here, okay, in order to produce the bendings and also the shear. But continuous beam, it contains more than one curve for the bendings and more than one curve or line for the shear force. So that's why it's quite complicated. It's much more difficult. Okay, it's more details in order to come up with its shear force and bending moments diagrams. So the code come out with two types of load arrangement, which is load set 1 and load set 2. Okay, for the load set 1, load set 2, it's actually is about how you arrange the load, how you arrange the maximum and minimum load. Remember, we have a maximum load which is 1.35 GK plus 1.5 QK, and then we have a minimum load that just consider about the permanent load. Kita consider GK saja for the minimum load. So 1.35 GK. Okay, so this is maximum, this is the minimum load. So for the load set 1, it mentioned here alternate or adjacent spans loaded. This is how we arrange the load. So alternate, that means you change from maximums to minimum, from minimum to maximum. Dia bersilih ganti. Okay, so that means if the first span you loaded with the maximums, the next span is the minimum. Then continue with maximums, then minimum, and keep continue for other spans. So that means this is maximum, this is minimum. Maximum that consider this load, and then minimum just 1.35 GK. Then we also can arrange by using the minimum loading first for the first span. So kita start dengan minimum pula. Okay, and then maximum. So minimums, maximums. Okay, so this is the two pattern of alternates, what we call it as an alternate load arrangement. Okay, for the load set 1, it have alternate and also adjacent. Adjacent, it means it's still alternate but 2 by 2 ataupun 2 by 1. So that means 2 spans. Okay, 2 span maximums, 2 spans maximums, and then 2 span minimum. and then continue for two span, maximum and minimum. Or might be start with the minimum load first for the two span, a two span minimum or two span maximum or minimum. And also it have other patterns that will be in these slides, okay, which is you can see here. This is the load arrangement for load set 1 that have alternates, right? So it begins with the maximum, minimum, maximums and continuous. So ataupun start dengan minimums then maximums, minimum. Okay, so this is the two case or two patterns load arrangement that we can estimates in terms of alternate spans loaded. Then we have another one which is adjacent, which is 2 by 2 here. Okay, so maximums for the two first spans, then continue with the minimums for the two span and continue with two span for maximum. Ataupun start dengan first only one span with the minimums, then continue with the two span of maximum and minimum for one span, and then continue with two span for the maximum. Or might be start with the two span minimums, maximums. Okay, as long as it have an adjacence between two spans maximums, two span minimum or one span minimums. Okay, so this is three patterns, okay, in the load set 1 in terms of adjacent spans. All right, so we have another one which is load set 2. Load set 2, it have all loaded, all spans loaded. Okay, so that's mean all the spans, how many spans that you have here, okay, doesn't matter. So all of it will be loaded as the maximum load. So all its mean all loaded with the maximum load, okay, which is 1.35 GK plus 1.5 QK. Okay. Tak ada, jangan buat minimums all loaded is a minimum. No, we go still for a safety, right? So we consider all will be the max load, okay, for the whole beams. Then in a load set to also have alternates. Again, alternates. It can start with a maximum, minimum, maximums, or might be start first with the minimums. So for the load set to, this is samples of the patterns. It have the first case we loaded as the maximum load for the whole spans. Okay, and then the second case, this is for alternate. This is for all loaded. For the alternate, it can be arranged by these two types here. Start with the maximum, minimums, ataupun start with the minimum, then continue with the maximums and so on. Okay, so you need to remember how we arrange of this load arrangement, especially for the load set 2. Okay, because so for this structural analysis, we just focus load set 2 for this subject. Okay, so you just need to remember we have all spans loaded with the maximum load, and then we have alternate span. So alternate, it can start with a maximum then minimum, or might be start with the minimum first then continue with the maximum, minimum. Okay, so each of the cases here will produce different shear force and bendings moment. Because of the first case is loaded with a maximum load, so it will produce these kinds of which is difference value, okay, will be produced compared to the load case 2 and load case 3, because load case 2 it consider the maximum first, while the load case 3 it consider the minimum loading, okay, for the first band. So the combination or compilation for all the load cases for its shear force and bending moment diagram, we call it as the envelopes here. So we have two here, shear force diagram envelopes and also bending moment diagram envelope. So you just plot load case 1 for the shear, okay, plot load case 1. Load case 2 for the shear, okay, plot at the same graph paper, okay, at the same axis. Same goes for the bendings. Okay, bending for load case 1, plot for the load case 2 and 3. How to differentiate is it can be used different color. Kan, load case 1 aku nak guna color biru, load case 2 guna color merah, load case 3 guna color hijau. Or might be you can use different type of line. Might be load case 1 use a solid line, load case 2 use a dotted line, load case 3 use a dash line. So this is how we make a differences between the load cases. From these envelopes, we can know which cases that give a maximum shear and give a maximum bendings. Okay, so kalau lihat sini load case 1 all loaded with a maximum, but it doesn't mean load case 1 will give a maximum load. It doesn't mean the load case 3 might be will give a small value, will give a low value for the shear or bending moment, because you can see from the envelopes here. Okay, let's say this is the maximum shear at these columns at the grid lines too. This is the support reactions. Okay, at grid lines 2 here. It shows here that blue color and red color produce the maximum Vmax, right? So that's mean load case 2 also have a potentials, okay, to produce the maximum shear force. Okay, same goes for this support here. So color hijau, color biru. So load case 3 also have a potentials, okay, to give a height value for the shear force. Okay, so from these envelopes, you can use the value here, okay, in order to design the shear links. So there are two kinds, there are two methods for design. Either you just use the highest one, the highest value for the Vmax in order to design for the whole shear links, in order to design the beams, okay, according only one Vmax. Okay, so katalah Vmax ini hundreds kilonewton. So semua shear links dekat beam, continuous beam ni akan guna 100 kilonewton. Might be there's another one method, another one method that more details because you want to go for economics. Mana yang low shear, you will provide less numbers of links. Mana yang tempat, mana yang spans that have a high value of shear force, you provide high numbers of reinforcement, which is it's more details. Okay, depends on the projects. Same goes for this bending moment. You can see here, kalau shear, the shear force only occurs at the supports, right? Then if you look at the mid span here, the V is equal to 0. Okay? So the V is equal to 0, but it's different Okay, with the bending, we have a bending moment at the midspan. We have a bending moment at the support. This is the support here. This is all the bendings moment at the midspan. So we have a moments max at midspan, and also we have a moment max at support. But this is only the V max at the support, while the shear force at the midspan is a 0. Okay, so kalau dekat support, so this will be the moment max, okay, which is produced by the load case 1. Okay, so kalau dekat mid span, so the load case 3 here produce the maximum spending moment at the mid span. So same goes for this one. We will design the main reinforcements according to the moment max at the supports, and also we design the main reinforcements, okay, according to the moment max at the mid span. Okay, so if you look at these cross sections of a continuous beam, so let's say this is the support, this is the support. So we have a main reinforcements at the support, and also we have a main reinforcements at the midspan. Okay, so this is how we design. So this is max for the support, while this is for the midspan. Okay, so that means this kind of envelope you need to do some exercise, especially for your projects. So that means for each of continuous beams, you need to come up with these 3 cases. Each of the beams, okay, each of continuous beam, you have to come up with all these load cases in order to plot this kind of envelopes. So if you look at for continuous beams, okay, is quite difficult actually. Okay, kalau simply supported, how you determine its supports reaction is quite simple, right? It have a 2 unknown here. Okay, from the loadings that apply on it. Okay, you can identify what's the RY, what the support reactions for the simply supported. But for the continuous beam here, for the continuous beam, it has several unknowns here, many unknowns here. Okay, so because of many unknowns here, it's quite complicated. Okay, you cannot just simply defines the RY same like simply supported here. So that's why there are 3 methods here, okay, in order to obtain the shear force and also bending moment, especially for the continuous beam. So we have a 3 method here. The first method is the moment distribution method, which is we also call it as a modified stiffness method. So this method you already learned before in the structural analysis subject, kan? Oh, tu macam dah tak ingat kan. So which is in this method you need to distribute the moment. Okay, it should be at least 5 repetitions or more than it. Okay, so the columns according to the supports, the tables and so on. Okay, so dah ingat-ingat semula kan. Okay, so then we have a second method here. It's quite simple, so that's why we call it as a simplified method, that using a table 3.5 in British Standard. So this is your job to find out where's the location for this table? Table 3.5 in BS. Okay. The third one here is lagi simple, lagi senang, just using software. Okay, but we not go for software, right? So this is the basic things you need to know before you can apply, you can use apa ni, with the software, um, especially okay once you become an engineer. Okay, so kalau simplified method is quite simple. We can just refer the tables in order to know what the shear force and bendings moment. Okay, so we go one by one here. So the first method is the moment distributions method here. Okay, so this distribution distribution method usually more than 5 repetitions. Okay, lagi banyak repetitions, you punya value will be precise, kan? So there are several factor or parameter that you need to know before you can use this moment distribution methods, which is FEM. Kalau ingat lagi, what is FEM? Fixed end moment. Okay, and then carry over factor, COF here, how you carry over, how you distribute it. It can be half from the moment or might be just zero distributions. So FEM, it depends on the loads there, okay, which we consider it's a fixed supports. So might be for this uniform load, it will be WL power of 2 divided by 12. This one also divided by 12. And then if the case for the point load, so point load, berapa equation? It just plays around with the equation according to the types of load that apply on that span, which is span by span, because we have a continuous spans, right? Continuous beam. That means it have a more than one span. Then member stiffness factor. Stiffness. So the symbol for the stiffness is a K. Okay, so remember what is K? So 3EI divided by L ataupun 4EI divided by L. What is E? Is the E modulus of elasticity. What is I? I is the inertia. That is from the cross sections. I is equal to BH power of 3 divided by 12. Depends the cross sections of the beams. Okay, so this is the equation for the stiffness. Okay, so this is all, but not all actually. It just a part of a fixed end moment, which is other than these kinds, other these types. You need to search, okay, might be from the Googles ataupun you buka balik nota structural analysis. There will be other types of loading. Examples. So for the spans that have a point load here, okay, let's say for these continuous beams, this is first span. Let's say there have a many spans here. This first span is loaded with the point load here, but it's not eccentric, it's not center. It have a length of A and length of B here. So that means you need to analyze these first spans, okay, to be this FEM, okay, to be this FEM with the end moment is equal to P A power of 2 B divided by L power of 2. Kalau dekat second spans, uniform load, so all of these uniform loads. Okay, so but you still need to analyze span by span. So for these spans, you have to use of these equations. WL power of 2 divided by 12. This one also estimate for this one and also for these spans according to the load. That is will produce different equation. It have a lot of kinds of loading. Okay, you can match kan. So sometimes there are case that have a combinations of load. Ada uniform load, then ada juga point loads. Okay, so how to calculate it FEM? Same basic thing here is the combinations, right? So we have dia punya FEM is equal to WL power of 2 divided by 12, and then plus might be it's not eccentric here. There are other case dia betul-betul centroids, right? You kena cari what's the equations, okay? If the point load is pointed exactly at the center of the span. Let's say these examples, sebab ada equations kan. This is examples for the point loads that is not at the centroid here. So plus it have a point load, so P A power of 2 P divided by N power of 2. Okay. Then we have stiffness. So macam mana nak dapatkan stiffness? So how to know what's the value for carryover factor? So for the carryover factor, it's quite simple. Either you distribute half of it, or might be there's no distributions. So just zero distributions here. So for the stiffness, it have two types here. Okay. 3 EI divided by L and 4 EI divided by L. So how to how to choose these two stiffness here? It depends of its locations and also its support. For the case of far end member pin or roller and support kat hujung ni, okay, at the end of the support, okay, if pin or roller, the stiffness for that span is a K is equal to 3 EI divided by L. Okay, so that's why stiffness AB is a 3 EI divided by L. If the far end support here, the end support here, pin or roller. If the support is a fix here, you need to use 4 EI divided by L. Okay, 4 EI divided by L. This is the fixed one, so that's why the stiffness for the DC is, or stiffness for the CD, DC sama lah, 4 EI divided by L. And then 4 EI divided by L also for the internal member. It doesn't matter how many numbers of internal member, as long as internal spans that should be 4 EI divided by L. Kalau ujung ni roller, so that means the stiffness is 3 EI divided by L. The internal member is 4 EI divided by L. The support, pin or roller is 3 EI divided by L. Can you understand me? Nak cakap kan? Faham tak? Okay. Then we have another one, distribution factor or DF. So DF is actually from the stiffness, okay, which is the ratio, the stiffness divided by total of stiffness. So total of stiffness here is a stiffness side by side. Okay, let's say tadi pins kan, dia punya stiffness 3 EI divided by L. So this stiffness 4 EI divided by L. So that means this is dia punya supports. So ni semua columns, right? All of this support. So the distribution factor is K divided by total K. So distribution factor for AB, okay, is a 1 here because 3EI divided by L, which is divided by total stiffness. There's no stiffness here, right? So that's why divide by 3EI divided by L plus 0. This is distribution factor for AB. While for distribution factor for BA, BA, which is 3EI divided by L for this pants, right? And then divide dia punya stiffness side by side, which is this side is 3EI divided by L plus another side is 4EI. So 4EI divided by L. So same goes for other apa ni? For other supports, for other point. Okay. Then we go for these examples. So in this example, it shows the layout here. You need to calculate the maximum shear force and bending moment for beam B, grid line 1 to 2. So this beam B, grid line 1 to 2. So this is the beam that you need to focus. Tak payah tengok beam lain. Okay, it mentioned here that the slab is made of precast concrete slab. So the unit weight of concrete is 25. It also shows here that the precast concrete slab is put on the beam here. So that means this beam will support slabs. Okay, there's no brick information here. So just ignore. There's no loading from the bricks. Lain-lain pun tak ada kan. So this is the only loading, okay, that the beam will be will support with the thickness of the slab here 175. So sama the concept here. What's the load that will be carried by the beam? It should be come from the slab. So you need to know how the load the slab distribute to the beam B grid lines 1 to 2. So lihatlah dia punya types of slabs, right? Is it one-way slab or two-way slabs? So the Ly is 7.5, Lx is 3 here. So please help me calculate this one. Ly divided by Lx dapat berapa? Anyone? 7.5 divided by 3.
2.5.
2.5 So 2.5 so jadinya one way slabs, right? So make one line parallel to the Ly here. So this is how the load from the slab will be distributed to this beam. Okay, so yang lain-lain sama je. Okay, calculates the load from the slabs according to its thickness. What is the material for that slabs? Okay, so the thickness 0.75. What's the material for this slab? Is made of concrete. So this is the unit weight. So QK based on the function, the purpose of that slabs. So in this case, in this example, it's already multiply with the safety factor, which is 1.35 GK plus 1.5 QK. Might be you want to do the calculations, just use the original GK, QK, tak payah darab dengan safety factor pun boleh. At the end nanti nak darab dengan safety factor pun boleh. But this example, dia dah darab siap-siap. Dia dah multiply with the safety factor first. Then the load here, which is 10.41, which is will be distributed for the whole slab. Tapi beam B just carry a portions, right? Half of the slab's load. Okay, so that's why for the beam B here, you need to calculate the slab distribution, which is 10.41 multiply with the 3. That means half of 3 here is a 1.5 meter. Another half here is a 1.5 meter. Okay, so this is the area that the beam will be will support the load from the slabs. Okay, so area ni saja. Okay, yang lain samalah. Berapa dia punya beam self weight, depends on its cross sections of the beams and also what's the material for that beams. Then multiply with apa ni? Safety factor here. Kalau beams tak ada QK, right? So that's why the total load for the beam here, okay, is the ultimate load from the slab. Okay, this one apa ni, already calculate with the safety factor, which is 31.23. Then add up with ultimate load for the slabs. Okay, ultimate load for the slab here, which is 2.5 multiply with 1.35. So this is the total of the beam B. Beam B grade line 1 to 2 is just a simply supported beam. So this is simply uniform load, 34.61 kilonewton per meter. Punya length dia 8 meter. Betul tak? 7.5 ya. $7.5. So from this load arrangement, load distributions here, you need to come up with the bending moment diagrams and also shear force diagram. How to plot this one? Either you find out what's the reactions, right? What's the reaction? Or might be use the equation here. Okay, kalau shear force WL divided by 2 for the bending, so WL power of L the power of 2 divided by E. Okay, ataupun you need to determine the support reactions here, right? So let's say find out the moment at these points. So the moment, let's say this is grid line 1, this is grid line 2, moment at grid line 2. So the moment is come from these forces, right, which is 34.61 multiplied with its bands, and then it should be half of it. Okay, make it as a point load. Half of it will be turned to this point here, which is 7.5 multiplied with 0.5. Another 7.5, right? Okay, in order to make it as a kilonewtons. And then you have another one forces here, Ry. So Ry will be brings to this point here, okay, for the moments, either positive or negative. Let's say this is anti-clockwise negative plus Ry, dia punya length to be at this point adalah 7.5. That is equal to 0. So from this equation, you will get the value for Ry. From Ry, you need to make equilibriums in Y, right? So which is Ry1 plus Ry2 is equal to 34.61. You already know the value for Ry1, so then you can know what's the value for Ry2. From all of this Ry, from all the forces, you can plot manually for bending moment diagram or for shear force diagrams. Okay, so this is basic thing. I assumes that you need to know of this basic thing, how to come up with shear force and bending moment for simply supported. Then this is an example for continuous beams. Again, for continuous beam, it's quite complicated. In order to produce the shear force and bending moment diagrams, you need to do the moment distributions method, moment stiffness, or might be simplified method by using the tables of 3.5 in the British standards, right? Okay, so in these examples, it mentions here, okay, to determine the shear force and bending moment envelopes. Nampak envelopes kat situ kan? So that means it should come from 3 cases. Okay, the shear force and bending moment should be from these 3 cases. Okay, for beam 1A to E. There will be a layout. Okay, supposedly there will be a layout with the slab thickness of 150 and the brick wall. So the brick wall that the beam should support, and also the thickness of the slab. So that means there will be a slab distributions to the beam 1A to E. Okay, so beam 1 here, A to E. So inilah beam yang kena fokus. Okay, so how the load transfer it? So determine what the types of the slab, one way or two way. Okay, different types of slab will distribute different way. Okay, kalau lihat sini kan, mesti ada expert kan. This is LY, this is LX. Simbol pun dah tegang-tegang bagi kat sini. Of course lah, it should be one way distribution here. So that means just half from the LX here, from 3 meter here, okay, will be transferred to this beam. But you need to know what's the N value, what's the load here, okay, which is the GK and QK of the slabs. So sama je. Okay, kalau lihat contoh ni, okay, it calculate the slab. Of course lah, you need to calculate the slab first, right? Because it will be transferred to the beams. In this case, it just maintain QK here. It just maintain QK here. It just maintain GK here. So this is the GK. It just maintain GK and QK. You can multiply with the safety factor first, or just let it just GK and QK first. At the end, barulah darab dengan safety factor. Boleh juga. Okay, so this is other examples. Same goes for the beam here. Okay, you need to transfer. You need to distribute the load from the slab, which is with the N value here, 5.25. Okay, just half of the length, just half the 3 meter, right? Okay, so then also for the QK, okay, half of the LX will be transferred to the beams. Then it shows here that this is the GK, this is the QK without any safety factor, right? So because we want to come out with load, 3 load cases that have a maximum load, that have a minimum load. So this is how the tables wants you to understand that we have all the spans. Okay, span AB, BC up to DE. So what's the value once we calculate as the maximum load here? So for the maximum, it will be 33.72, okay, which is considered for the GK and QK. So this is the value if we calculate for the minimum. So that means it will be 24.72, okay, the value for the minimum slot. The value for the maximum slot is 33.72. We have a 3 load cases here. So load cases 1, that means all the load loaded with a maximum load. So that means all span will be supports the load 33.72. Okay, so kalau load case 2, it start with the maximums and then minimum. So that's why maximum span AB 33.72. Span BC 24.72. So same goes for load case 3. It starts with the minimum, then maximum. So this is minimum, this is maximum. Okay, so if you look at here, this figure, this is loaded with all maximum load, which is load case 1. Okay, from the load case 1, you need to come up with its moment distributions methods. Okay, so in the moment distribution methods, okay, you need to know the stiffness, right? Okay, so the stiffness is a 3EI or 4EI divided by L. You need to arrange according to the spans there. What the types, what the far end support for that spans. Is it pin or roller? So that's mean 3EI divided by L. Kalau fixed atau internal member, it will be 4EI divided by L. So I here, it based on the cross sections of the beam according to these equations here. So this is the I for all the beams. So ada juga case dimensions. This is difference I1. This is difference I2. This is different I3. Why these three difference I for this continuous beam? Because it consists of different beam size, consists of different beam cross sections. So katalah I1 dia 150 kali 300. This I2 is quite bigger here with the depth of, let's say, 500 to 50. This one I3 is about 200, 400. So that's why you need to identify that inertia or that beam, is it uniform or standards for the whole span for that continuous beam or not. Okay, so in this case, the beam only have one size, right? Balik soalan. Kan, dia ada satu size je ni. So that means from grid lines A to E, semua sama size. 300 kali 500. That means only one value for inertia. Then from the stiffness, you can calculate for its distribution factor. Remember, for the distribution factor, which is K divided by total stiffness of its side by sides. Okay, so that's why at joint A and E here, for the last one here, there's no stiffness, right? Okay, at one side, so that's why it's equal to 1. Okay, depends also, is it 3EI or 4EI? Okay, then the rest you need to calculate what the stiffness here, and then which is this stiffness K divided by this total stiffness, which is total K, in order to come up with this distribution factor. Okay, this is examples. Dah ingat balik. Ni dulu yang korang buat masa structural analysis kan. that will be applied again in this subject. So that's why before you can register for this subject, you need have a knowledge, basic knowledge from the structural analysis. Tak ingat tak apa, pernah belajar dulu kan, buka balik buku. Nota dah hilang, cari balik. Okay, so no excuses. Okay, especially will be applied in the project. But once in the test or ataupun quiz ke ataupun finals ke, so we will because of times, right? We will make limitation for the spends. Okay, kalau banyak spend ni, lagi banyaklah you punya calculations, right? Let's say we provide give a question just for the two spend, but still you need to come up with these kinds of tables for the distributions. Okay. So look at the first row here. The first row here is a part by part. Okay, part A. This is the part A that have a span AB. This is a part B that have a span BA and BC. Sama lah macam lain ni, kan? Okay, DF, distribution factor, which is K divided by total K. So that's why you need to calculate this one first. Okay, so just list out what you have already calculated for the DF based on stiffness. And then FEM, so ni lah FEM here, which is this one you consider as a these kinds of loading. Okay, so for this pattern, the equation is WL power of 2 divided by 12. This is which is the load case one, it loaded with the same maximum load. So that means all the spans will have the same FEM. Okay, but the W is here, it based on the maximum load, right? So it should be based on 1.35 GK plus 1.5 QK. So that's why kita guna 33.72. Same goes for other span here. Okay, is it positive or negative? Because moment have a positive and negative, right? So let's say bawah positive, atas negative. So that's why we have a moment positive and also moment negative. Okay, so how to distribute? Refresh balik. So which is this is negative 179.83. So tak ada, it doesn't have any couples here. So directly for this moments multiply with the distribution factor 1. Remember, if you multiply it's negative, so that means once you put it here, the answer it should be positive. Once it's positive, you need to put the answer here to be opposite signage, which is negative. Okay, so this one dapatkan dia punya total negative 179.83 plus 179.83 is equal to 0. Multiply with this one, so that's why 0. Sama juga macam yang lain. So distribute, is it 0 or half? So this directly 0, and then half of this one is 89.82. Same goes to other columns. Okay. So then you need to repeat, right? So that is why it mentioned that the repetition at least 5 or more than it. Lagi banyak repetition, lagi precise. It's more precise. Okay, so based on this one that you already distribute 89.92, okay, plus a 0, there's no here. Okay, so multiply with 0.43, you will get negative here. Remember, if positive, it should be negative here. opposite signage here. So same goes once you multiply with 0.57, so you will get off this answer. Okay. Then again, you distribute this one. So this is directly just zero of it. Okay, at the end it's just a zero. So distributes half of it. So same goes for other steps. Should be 5 or more than 5 steps. In order to know is it correct or not, precise or not, again, at the end, okay, for the end moment, it should be same value, which is 231.21. The other side also the same one, but the difference is a positive or negative. Kalau ada salah signage ke, you need to check against your calculation, which is 179.83 plus 89.92 minus 38.54. You will get this value. So this 231.21 is the end moment for each of the support reactions here. So this is 231.21. There will be a positive and negative according to the clockwise or anti-clockwise. This one 154 4.14 kan, sama je lah macam yang lain. So you already have all the value, all the uniform load, all the moments. From this one you need to come up with the cut sections method actually, in order to know if supports reactions. Okay, so this is the load distributions, okay, which have a end moment here at each of the supports. So in order to know what's the shear force here, what's the bendings moment here, you need to use the cut section method. Ingat lagi tak cut section method? Sama juga cut section method ni you dah belajar dalam structural analysis. Kena refresh lagi satu kan. Cut section method, that means you analyze sections by section. That means you cut these sections, cut this section, cut this section. So analyze section by section. Let's say for the first sections, I have a support here. Okay, let's say this is a V1, this is a V2. Okay, so then it have a moment 231.21. Load 33.72. Okay, same basic calculation as a simply supported beam here. Find out the moments, let's say at this point. Okay, so this is clockwise, so 231.21, and then make it this load turn to this point here. This is anti-clockwise, so negative 33.72. Make it as a kilonewtons, multiply with the length, and then from the length also you need to make it half of it, right? Okay, and then you have one unknown here, which is V1. Turn it to this point here. This is clockwise. Okay, so plus V1 is equal to 0. You already know what's the value. From this, you will know what's the value of V1. So make a equilibriums of Fy. So V1 plus V2 is equal to 33.72 multiply with the span here. So replace the V1 value, you will get the V2. So this V1, V2 is a value that you will be plot in the graph for the shear force diagrams. And then for the moment also, what's the value for this? moment. You need to calculate sections by sections. Okay, kalau you lihat at the same support here, it have a 2V. This is, let's say, V2A, and another one is a V2B, because when you cut these sections, it's also have a supports, the same support here. Okay, so kalau I buat the second span, tadi V kita guna V2A, so might be this is V2B, this is V3A. So it has a two end moment here, 231.21. This is 154.14. So sama juga, dapatkan moment, dapatkan shear. So that's why V2B will be plotted at this point, and so on. Okay, so you need to repeat this calculation for the next case. Load case tu sama juga, but the difference is this is maximum, which is dia punya load consideration here is a maximum for the first span 33.72, and then for the second span dia punya loading adalah minimum, which is 24.72. Okay, sama juga yang MCD guna maximum, MDE guna minimum. So that's why you will get the difference load here. Okay, this is the moment from here. So repeat the same calculations. Okay, what's the end moment here? From this one, you need to do the cut section by sections in order to plot shear force diagram. Same goes for other load cases. Okay, load case 3 pun sama. At the end, you will come out with this kind of envelopes. So these envelopes is the compilation of load case 1 and load case 3. Okay. So look at for this shear force diagram. Let's say this is the highest, the Vmax here. Okay, might be you just refer for this Vmax in order to produce the shear length spacing, the diameter for the shear length for the whole continuous beams. If you look at for the moment, ada dua moments. Moments for at the midspan, maximum moment at the midspan, and then which one the maximum moment for the support? This one's right. Okay. This one also. That means this is the moment max at the support. This is moment max at the midspan. This will be used in order to design the main reinforcements at the support, the main reinforcement at the midspan. Any questions? Ada soalan before I terus proceed pada simplify?
Doktor.
Ya.
So untuk yang tadi kita memang kena buat tiga case.
Yeah, once we talk about envelope, so kita kena buat semua 3 case. Sebab kita nak tahu case mana yang memberikan nilai maksimum. Tak semestinya case 1, tak semestinya case 2 or case 3. So that's why come up with this envelope. Tapi bila you dah kerja nanti tak adalah software. Okay, will you can get all the data right from the software, but this is the manual, the basic thing that you need to know. Okay, even kalau I pernah pergi kursus UTM yang bagi talk Prof Dr. Ramli, I think, tak ingat sangat nama dia. He mentioned that dia punya consultants still use this manual calculation. They go for this manual envelopes. Kan? So but some of the designer they just skip these steps actually. Dia buat satu case je all loaded. Depends. Okay, again depends your projects or your majikan kan, you punya top designer, how they ni dia punya practice macam mana dekat consultant tersebut. Okay. Alright, ni senang kan, simplified method. Nak guna simplified method lah, guna table je kan, tak nak guna moment distribution method tadi tu. But it have requirement that need to fulfill before you can use of this simplified method. Ada syarat dia. Nak senang mesti ada syarat, kan? So this is the requirement. This is the requirement. The first thing, the beam should be approximately equal span. Tadi continuous beam, semuanya lebih kurang sama span kan, 8 meter semua sama. Okay, pass. Equal span. Kalau ada satu 15 meter, Allah, satu dah 15 meter kan, baru nak guna simplified method. Tiba-tiba ada satu span 15 meter. That should be the differences, the variations in span length here, it mentioned here, should not exceed 15%. Kan, kalau within this range, so that means you also pass of these requirements. Okay, and another one here, the variables actions QK may not exceed the GK. So that means if QK less than GK, okay, you already fulfill the next requirements. Then the last one, load should be substantially uniform, distributed over 3 or more spans. That means these tables only for spans, only for 3 or more span. Kalau 2 spans, tak boleh guna tables ni. Kena guna moment distribution method. Kalau 3 span, 4 span, 5 spans, more than it, you can use of this simplified method. But you have to fulfill all these requirements. Okay, so this is very important, okay, before you can use this simplified method here. So ada berapa requirement ni kan, so kena fulfill all of it. So how to use it of these equations of this table is quite simple, but you need to understand the locations, okay, the locations for that moment here. It give a moment and shear equations here. It mentioned here at outer support moment 0. So outer support yang paling last sekali, and support moment 0, of course moment 0. I try change color. Okay, so moment 0, so moment kat sini 0. Kan, it mentioned at outer support. This one also 0. Ada lagi satu span. Okay, this one also 0. So near middle of end span, this is the end span. This also end span. Middle of end span. The moment is 0.09 FL. So that means you can just plot using these equations in order to know what's the moment value at the middle of this end span. Use of this equation 0.09 FL. So you boleh buat sketch lah, kan? So just masukkan saja nilai 0.09 FL, F berapa, L berapa dia punya span, F is the force, dapat nilai moment kat sini. Senang kan kacang. At first interior support. Kalau tadi sini adalah outer support, So this should be the first support. This should be the first support, which is the moment is a negative. Remember, moment we have a positive and negative regions, right? So negative 0.11 FL. So negative, of course, it should be upward, right? So this would be moment here is negative 0.11 FL. Just substitute the value in order to know what's the point moment here. Okay, at middle of interior span. So kalau ni end span, the rest will be the interior span. This is interior, this is interior. It doesn't matter how many numbers of interior spans. So 0.07 FL. So we back to positive here. 7 FL. At interior supports, kalau this is the end support, this is the first support, it same. Okay, for the both side, it's mirror. So this is will be the interior support. So at the support here is a negative one. Naik balik negative, which is it keeps continue according to the locations here. Okay, so kalau shear pun sama juga. So at outer support, shear, outer support, this is also outer support 0.45. This is also 0.45. Dah dapat dah plot satu ni. Dah dapat dah plot shear force diagram. Okay, so just replace the value. Okay, so sama juga at first. There's no shear force, right? V is equal to 0 at mid span, remember. So that's why there's no value here. The shear only at the support. So this is first support. Okay, first support 0.65. So 0.65. This one also 0.65. Okay, at interior support, you have other interior supports here. Okay, so you have to just follow the tables here, which is F is a total design ultimate load, so which is the maximum load. L is the effective span. Okay, so this is how the simplified methods. So this is for the end span, for the interior spans, according to the bendings and also shear. Okay, so bagi lagi examples. Banyak example bagi. Kalau you lihat dalam auto system, I also give you additional examples. Okay, I also give you additional examples, which is you can refer. Okay, rajin dengan tak rajin je kan, semua dah bagi. Kalau rasa tak cukup, try buat try search ataupun you from the layout this one also you can do your own exercise. Macam yang selalu saya cakap, kalau dalam contoh kan, dia suruh you design beam 1, loading dia begini. Okay. So you nak practice, so try design beam 3 kan. What's the envelope would be plotted, what's the value, try design beam B, beam C, semua design, barulah experts kan, barulah terror, betul tak? Okay. Okay, so for these examples that use simplified method here. Okay, so dalam simplified method ada F, ada L kan yang you kena replace. So you just calculate for the F value, which is the maximum ultimate load, and then untuk L you need to multiply its spans, length. Kalau ni length dia lain 9, so that means this will be difference F for this point here. Okay. So just follow the tables, okay, in order to plot. Ni dah plot lah ni. Ni dah plot lah ni shear force diagrams. Tak payah nak buat moment distribution method. Tak payah nak buat cut sections in order to know what the shear force and bending moment diagrams. Kan? Dah dapat dah dia punya moment ni semua. But it should fulfill all the requirement before you can use of this simplified methods. Okay. Right. Okay. Sampailah penghujungnya. Tekak saya pun dah kering, sakit. Okay. So last one is about moment redistributions. Okay. What is moment redistribution is? Actually it's like reductions of numbers of reinforcement. Kita macam bagi discount dengan load estimation, dengan load distributions yang kita dah buat, because there's because of congested of reinforcement. There are many reinforcement at certain points, especially at the intersections. Okay, especially at the intersections between beam and column. So if you look at here, these beams, okay, and then these beams, okay, actually this is a one continuous beam here. And also have other sides of a continuous beam. Each of the beam have its own numbers of reinforcement. Each beam have its own diameter of reinforcement. Depends how many load that it should be carried. Kalau high load, so that means there will be a high numbers of reinforcement. The size also will be bigger, okay, according to the load that the beam should be carried out. At the center one here also have a columns. Columns pun ada dia punya reinforcement sendiri. So you can imagine how congested all these intersections, right? How crowded all the reinforcement, nak kena ikat, nak kena susun, nak kena arrange with the spacing of the links also. So that's why the code also come out with moment redistributions. That means from the 100% from the old bandings moment. Remember, for the bandings moment, we provide the main reinforcements, right? Okay. So that means we give a discount, okay, for the moment redistributions. Once the moments reduce, that means we can reduce the numbers of reinforcement. That means we can use smaller size, smaller diameter of the reinforcements. Okay. The moment redistributions here, it can be up to 20% or 30%, which is depends what the class of the reinforcement. Is it class A, class B, or class C? So that means you need to know what the class is. Okay, what A, B, or C. Okay, so kalau dalam soalan, they mentions that need to do the moment redistributions. So that means from the original moment, you need to come up pula dengan moment redistributions. It mentioned class A. Okay, so that means you punya redistributions there should be up to 20%. So kalau dalam soalan tak ada mention about moment redistributions, jangan buat. Tak payah buat. So just give a original shear force and bendings moments. Okay, for that calculation. But if at the end it mention buat pula moment redistributions, so that means you kena buat dia punya reductions. Okay, this is examples here. Okay, kalau you lihat the originals, it based on example 3.5, you can refer back the previous example. From the bending moment diagrams, the original moment at support B and D is 231.21. So boleh pergi balik, nak bagi faham kan. Okay, nampak sini dekat support. Support B, support D. The moment, this is the original moment, which is 231.21, but we give a moment redistribution, we give a discount to it, which is with for 20% here. Let's say this is the class A. Okay, let's say this is the class A. So this is the moment after redistributions. Only 184.97 and only 123.31 here. So this value, you need to calculate back dia punya shear force and bendings moment. Tadi dah dapat kan? Sini tadi berapa? 231.31. Okay, so dah reduce up to 184.97. Replace in the cut sections. Ni contoh solution cut sections. Okay, dekat example 3.5 tak ada contoh cut section kan. Ni dia bagi contoh dekat 3.6. But this one use the value of after redistribution. So you get the new VA, the new support reaction, each of the support. So this is the new one. From this new value, you can plot back, okay, according to all the cases, all the cases. Okay, so this is the shear force diagram and bending moment diagram once you do the moment redistributions about 20% here. So you can make a comparison. Original SFD tadi berapa dia punya plot dia. Bending moment berapa dia punya plot dia. Tadi dapat kat sini 231 kan. So this once you reduce at the support, the rest also will follow. Okay, so that's it. Habis sudah end of this chapter 3. So see you again after 1 week, right? Holiday for Hari Raya. Then we will continue for chapter 4, okay, on design of beam, and there will be also the importance date for the test. The test will be included up to this chapter, which is chapter 3. All right, so that's it for today. Any questions? Are under attendance in the systems? Ada soalan tak? Orang? Any questions?
Tak ada.
Tak ada, doktor.
Okey. Tak ada sebab sama ada memang faham ataupun nak buat exercise dulu kan, baru faham. Okey. Okay, so I stop sharing. If you don't have anything, so I stop the class right now. See you again after Raya. Selamat Hari Raya semua. Bye.
Selamat Hari Raya, doktor. Terima kasih.
Okay.
Thank you, Doctor.
Don't forget attendance in the auto.
Thank you, Doctor.
Alright.
Thank you, Doctor. Selamat Raya.
Hari Raya.
Thank you, doktor.